Yep. Hello everyone, my name is Bogdan Sirbu from FraunhoferIZM, and I will be talking today about TSV integration into silicon photonics interposer for next generation transceiver PICs. I will go fast through the introduction slides. We have seen this during the entire afternoon, so we are all aware of the exponential growth of traffic, and the downside of this fact is in terms of power. The best case scenario for the predictions for 2024 is that the data center use will account for 4.5% of the total global electricity usage. So one of the components that will provide higher bandwidth and smaller power consumption could be the silicon photonics transceivers. Here we have a forecast for the market. So the units are increasing every year, and if we look into the packaging, the actual silicon photonics chip is accounts of a small percentage of the total cost, and most of the cost comes from the assembly test, connection, lasers, and things like this. And we are facing several key challenges here in terms of assembly. So we need precise fiber alignment. We have to handle delicate and odd shape parts. We have different die attach with different CTEs. We need them to be reliable, and definitely more has to be done in terms of testing and standardization in terms to make everything to bring down the costs. Here we have seen it. We have seen this slide in Elad's presentation. So on the right side we have the different form factors for the new transceivers, and on the left side we see that we are moving towards the 800 and 1.6 terabits Ethernet standards, and this is expected to ramp up after 2021. A few words on the MASSTART project. Basically, here we are in line with the standard roadmap. So in the project we are targeting 3 WDM modules for 400, 800, and 1.6 teras, and Coherent transceiver. And basically our approach it's based on few key components such as the glass interface between laser or the PIC or fiber to PIC, which is based on glass waveguides, and they provide the spot size conversion and the pitch conversion in order to allow more I/O count. We are developing a 3D packaging concept based on TSVs, and we are developing a new generation of flip chip bonders to improve the speed of assembly, and we are performing also some wafer level evaluation of the devices. If we look on the competences in the consortium, we have some technology providers such as Leti, which is providing our silicon photonics chips, FraunhoferIZM, which are bringing the TSV technology, Team Photonics providing the WAFT, the coupling to the chip, and Almay providing the lasers. We have a design house which is putting all the building blocks together and assembling the entire demonstrators. We have some photonic assembly and testing companies, Tech developing the assembly machine, Tektronix bringing the testing equipment, and the University of Thessaloniki. bring in the testing, and we have some system providers such as Photonics, NVIDIA, and ADVA. And if we look into the Coherent transceiver packaging concept, we can see that basically the light is coupled through the watt into the silicon photonics chip. Here we have the modulators and photodiodes integrated in the silicon photonics, and on top of the chip we will have the electronics, so drivers and TIAs. And the entire concept is based on high-speed TSVs connecting, providing the connection to the DSP or to a PCB with the connectors. I will be focusing on the TSV development right now. So this is the first model we developed for our proof of concept. If the process flow is working when the photonic chip is fabricated at Leti and the TSV is processed at IZM. So this is the first test structure with going through 4 different TSVs back and on the back side and top side of the substrate, and we're expecting good results. And this building block is actually integrated in the final demonstrator. Here we can see the packaging concept with the TIA driver assembled on top of the silicon interposer, and we need to connect the electronics to the DSP through the PCB, and that is been done in this case through this building block. So we have the differential traces with a certain pitch matching the driver and TIA's pads, and on the bottom side we have the BGA connection to a PCB. And the results are promising for simulations up to 60G. And in terms of TSV integration schemes, so here we can have, as Stefan presented in the previous talk, we can have via first or via middle. So basically the front end in this case is done at the front end, metallization is done at Leti, and the back end of line at IZM. And in this approach, the TSV can be done before or after the front end metallization. And the second approach will be via last, where the back end of line is processed, and afterwards we need to the TSV will be processed. And in these 2 cases, we require temporary wafer carrier in order to process the backside metallization. And the third approach is backside by last, and here it's basically the back end of line and front end are processed, and the backside metallization is done in one step with the TSV. And this approach is very useful for sensors, for example, for sensor applications. So in our case, we will be focusing on the first approach. And going in the process flow more in detail. So basically the first step is the front end metallization done at Leti. The wafers are already at IZM, and here we already said that the TSVs will have a certain position, and here is marked, and this position has to be, it's a keep out zone, and the TSV is processed on the next step. And when we fill the via, we need a seed layer oxide that is covering the pads. Next step will be opening the pads of the front end of line from Leti and processing the top RDL layer, then passivation opening, and finally building processing the UBM on the top side. Next step will be to stack the wafer on a temporary carrier in order to allow the processing on the back side. We are grinding the wafer to the desired TSV thickness. In this case, it's about 100 microns. And we process the backside. So we put the seed oxide layer, metallization, and pad opening, and finally building the backside UBM. And the last step is the removal of the carrier wafer. For the first steps, tests of this process flow from the Leti wafers, we foresee this test reticle where we have several RF and DC tests, and basically the green metal layer is the front side metallization at Leti. The blue one is our front side back end of line, and the red one is the back side RDL at IZM, and we have several test structures. So we have the standard ground signal ground HF test structures with the calibration structure. We have some daisy chains going through all the RDL layers, and we have some 4-point probe structures for via isolation measurements and the resistance. And currently the status of this test reticle is the chip has been processed at Leti, is currently at IZM. We already etched the vias, and basically the test reticle, it can be seen here, and the current the next step will be to fill the vias and proceed with the next steps. And that was all from my side. Thank you.